What is functional programming, and what makes it different from other types of programming? Well, functional programming is a really large, really vast subject. But thankfully, functional programming is all driven by one key idea, one key principle that is both very simple and very elegant. And I hope to explain that principle to you in this video. But before we do that, I want to talk about a little bit of context. So functional programming is a programming paradigm. And a programming paradigm is simply a way of thinking about solving problems. I like to think about programming paradigms as programming tool sets. Functional programming has some specific tools that it uses to solve problems. And functional programming is a programming paradigm that's rooted conceptually in mathematics. And we'll see when I introduce this key principle that has its origins in mathematics. And finally, functional programming, because it's not a particular language, it's language independent, which means that while I'll be writing a lot of the code in a language called OCaml, you can really take the concepts that I cover and apply them to a lot of other languages, such as Perl and JavaScript. And there are more functionally oriented languages like Haskell and Lisp that the concepts carry very nicely into. So let's talk about what this key principle of functional programming is that I keep mentioning. And it's really very simple. The key principle is that functional programming thinks of all computation as the execution of a series of mathematical functions. So let me write that here. All computation is the execution of mathematical functions. Great. And so we can see here that this is a very succinct driving principle behind functional programming. And we can see where the name functional programming comes from. So what exactly makes functional programming different from other languages? To really answer this, first I have to cover what a function is. And you might have already seen what a function is before. A function in mathematics is simply a mapping from inputs to outputs. And I'll write some functions that we might see commonly in mathematics here. So for instance, I might see, like a function called f, and it might take an argument x. And it might say, well, this is equal to x times 2. And so this is a function. It maps numbers to numbers. So it would map the number 1 to the number 2, and the number 2 to the number 4, and the number 3 to number 6, and so on and so forth. Great. And I can also define new functions in terms of old functions, compose functions together. I could create functions like this one called g, which takes in 2 arguments, an x and a y. And I could say, well, g of x and y is equal to f of x plus f of y. And so something like g of 20 and 1 is equal to f of 20 plus f of 1, which f of 20 defined over here is simply 40 plus 2, and I get the answer 42. I can define functions lots of different ways. For instance, I could write the function h, and I could say h of x is equal to 1 if x is even, and 0 if x is odd. So this is a function that takes in all of the integers and maps all of the even ones to the number 1, and maps all of the odd ones to the number 0. So what makes these functions any different from the functions you might have written in a language like Java or JavaScript or C? Well, the most important thing about these functions is they have a particular set of restrictions. These mathematical functions can't change their inputs. So what does it mean to not be able to change their inputs? Well, let's say I had a function, h, let's use the example h of x. And let's say that h could change something about x, its input. Well, that would be like if I said, well, h of 12, what do I do with h of 12? If h could change something about the number x over here, then shouldn't h of 12 be able to change something about the number 12? And what does it mean to change something about the number 12? In mathematics, 12 isn't a variable to be changed, but rather it's a concept. It represents something about numbers. And so if I could just simply change the number 12, I would change a lot about the mathematical system that underlies all of our computation. So functions can't change their inputs. So as a result, functions in functional programming have certain restrictions that other functions in other languages don't have. And because functional programming represents everything as mathematical functions, that means we can't have any inputs changing. And that also means that we can't change any variables, because in order to change variables, we would have to represent that as a function, as the execution of a function. And we just said that functions can't change their inputs, so we can't change any variables. And this is a concept that's called immutability, where once we define a variable, that variable can no longer be changed. And so what does this mean for our programming styles? Well, that means we can't have things like counters. So if I wrote the following, x is equal to x plus 1, where x is a counter variable, and I'm going to update it when I run this line. Well, we can see that this isn't a function, and we're changing variables. So we can't have this in functional programming. So what else uses this variable reassignment? Well, loops do. So I could say for I is equal to 0, I is less than 10, I plus plus, I plus plus. I can't have this either because here we're setting a variable, and over here, every time through the loop, we're updating it. And we just said we can't reassign variables. So we can't have loops in our language. In fact, some people have said that functional programming is programming without variable reassignment. And this is quite accurate. And so we rule out a lot of possible computation or possible tools that we could use. We can't update variables. We can't have counters. We can't have loops in our languages or in our programs. So doesn't that seem kind of limiting? How are we supposed to solve the problems that require loops without using loops? Well, I like to posit two things. One, that we'll see later on that we can solve all of the same types of problems with functional programming with a fewer set of tools than if we had a more expressive language that had loops and counters. We can still solve those problems, even if we have to go about it in a roundabout way. The second thing is that because we have this concept of immutability, it's really not so much a detriment, but it's a trade-off. We lose some of the expressibility, we lose some of these programming tools in exchange for some benefits. And in the next video, we'll explore what the trade-off is in a bit more depth, what benefits we get for having immutability in our programs. But for right now, let's recap what we just said. At the very start, I said that functional programming is quite different from other types of programming. But it's a programming paradigm that's rooted in mathematics, that's language independent. It's all driven by this one key principle, that all computation is represented as the execution of a series of mathematical functions. And we said a mathematical function is a mapping from inputs to outputs. And we saw some examples, some very simple examples. We can see that they can get composed together. And we also said that mathematical functions can't change their inputs. So as a direct consequence of everything in our programs being represented by functions or the execution of functions, we can't change any variables. And this was a concept that we said was called immutability. And immutability rules out loops, it rules out counters, it rules out all variable reassignment. And as a result, I say, well, we lose some expressibility or some expression, some tools in our languages, but we get some benefits, which we'll explore in the next video.